That's great. Okay, hopefully, can you see it full screen now? Yeah,
Yes, we
I
can.
guess so. So, okay, thanks a lot for including our paper on the program. This paper is joint work with Alan Timmerman, that hopefully most of you know his work, and Max Young was a PhD student here at UCSD. So, this title, Gauging Hourly Economic Activity in Your Neighborhood, um, is about measuring economic activity at very fine levels of granularity. So if we think about economic activity, it's a fundamental object in much of the analysis that we do, and it has clear temporal and spatial components. So that if we have economic activity in London, is probably very much different than economic activity in San Diego. And even if we fix location, economic activity in January is very much different than in summer, so July, for example. But much of the economic research has focused on aggregate levels of economic activity. So this comes from data limitations and computational issues. But most of the measures that we have are aggregate measures in space and time. So quarterly US GDP or uh, annual state level GDP. Anyway, in one way or the other, these measures are always considered to be aggregated. So what we do in this paper is that we try to push the boundaries of these limitations and move towards these higher granularity levels. So we developed basically a model that allows us to measure economic activity at hourly frequency and zip code spatial level. So that's basically what we do in this paper. So this is going to be what we actually show. This plot is showing the economic activity in San Diego County, which is about more than 60 zip codes. And it shows the variation, but in time and in the hours of the day. As you can see from this star plot radar, there's a lot of variation both in space and in time. You have to read these in a way that blue means low economic activity and red means high economic activity. And you can see, of course, that during night economic activity, so this is, for example, 12 p.m., so in the middle of the day, and there's a lot of economic activity going on. But then as we move throughout the day, and if we look at night, 1 a.m., there's not much economic activity going on. Okay, so this shows that, and there's also a lot of change, like dynamic in the spatial dimension as well. Okay, so this is basically what we do in this paper. Here's the roadmap of the talk. It's gonna be data modeling and estimation methodology, and then we have a whole set of empirical results about what we find, how do we actually validate, and what we can do with it. Okay, so we begin with the data, which is really a key component of this project. So we use data at very different levels of both granularity and time frequency spatial recordings. So on one end, we have this new alternative data series, which are very granular and are these hourly zip code series, which are series on geomobility data, geolocational data, like food traffic, traffic flows. So these are, for example, food traffic is the number of visits to point of interest location. So you can think about it as proxying in the local mall, how many people in a given hour of the day, in a given day, were visiting that mall. So how many people were at Costco at between 1 a.m. and 1 p.m. and 2 p.m. on March 25, 2026. Okay, this is basically foot traffic. Then traffic flows does the same, but for car vehicle traffic. Then we have electricity usage, temperature data, and these are at hourly zip code level. Then if we move from hourly to daily, we go with we have credit card transaction data, which are not available at that hourly level. And then we also have lower frequency measures, which are standard economic series that we all know, like weekly unemployment claims, monthly payroll data, and annual GDP. So what we do in our data set is that we merge this new alternative data series with this traditional data series. Um, since most of economists, at least, we were not familiar with this new data, alternative data, even because they have been available only, I would say, after COVID, and so they are really new, and the empirical facts are kind of unknown. We document what do these series look like. What we discovered is that if you look at the intraday dispersion that this series have is huge. So that basically for traffic, for example, you have with respect to the mean, an excursion that is about 200% within the day. Okay. So and the same for traffic flow, but also electricity and temperature data. They have a lot of temporal intraday excursion. And one thing that appears from these plots is that these are the weekly cycles of this series. There's a lot of common patterns. So that basically, if you look at foot traffic and traffic flow, you have these peaks in the middle of the day, and then these drops during the night, and the same for electricity and temperature. And then, of course, you have some idiosyncratic component like traffic flow. You can see there's a double peak, which you can match with the anecdotal evidence of people commuting. So the first peak is people commuting to work is about 9 a.m. The second peak is people going back from work to home, which is about 4 p.m. While foot traffic peaks around lunchtime, like 1 p.m. So people that walk from office to have lunch. And then you can see also traffic flows during weekends is much smoother, meaning that you don't have the double peak of commuting to work. Okay. So basically, what that plot shows is, that there's a lot of richness in intradaily, hourly patterns, and that these series they actually show common patterns. Okay, but a big question that everyone might have is, but can they proxy for economic activity? Because you have shown, I showed you like very different series, like for traffic, traffic flows, weather data, temperature. So can they actually proxy for economic activity, which is what we care about? And yes, in the paper, we show that these series, they are correlated with traditional measures of economic activity, namely payroll growth, so that you can establish a link between changes in payroll and traffic flows, foot traffic, electricity usage for credit card spending data. Okay, so that was green light for us to go on and say, okay, we can use this data to extract economic activity. But then the question is, how do we do that? Because we know that we have documented some empirical facts, and so the question was how to set up a model to extract this common component. Okay, so and this is exactly what we do. We're building on this common component idea. We propose a dynamic factor model that decomposes basically this H observable, Y H means that these are hourly series. S means location, spatial location. I means series. So I means traffic flow, electricity usage, or temperature data, vehicle traffic. And TH is our age of day T. Okay. Then in the model, actually, we also have that age, the top age will be dropped because we have the full temporal scale that we consider all these series at different scales, meaning also credit card spending data, payroll at monthly level, and so on and so forth. So we decompose each of these series in two terms. You can think the first term is what we relate to economic activity, and is driven by this common factor. This LEA factor is our local economic activity component. And then the second component that we have in the series is an idiosyncratic component, okay? So that decomposes this observable series into two components, one related to economic activity and one not related to it, okay? And then we impose some structure on the economic activity factor. And specifically, we add the two components. One, which is this persistent mean component, which we model as a local linear trend model, and is absorbing much of the variation that we've seen. And then there's an additive calendar component to account for the fact that since we are dealing with these high frequency observations at hourly level. You have hour of the day effect, day of the week, holiday effects, seasonal components, and so the deterministic component is going to take care of those effects. Okay, and then the question is, okay, we have data. We know we can extract economic activity. We have a model how to estimate. Because here the challenge is that each series is hourly, so when you have hourly series in 1 year, you have approximately 9,000 observations. You have zip code levels. So for each series, each zip code, you have 9,000 observations. So if you have 100 zip codes, 4 series, and 9,000 observation every year, you can see how big, large dimension of this problem is. And so if you think about running a simple Kalman filter to extract that factor, that is going to be quite tough. So what we do is that we propose this two-step estimation. In the first step, we estimate the factor, and we do in two phases. So we do this spatial pooling, which is similar to what people do with convolutional neural networks, so that we combine information and we we gain in efficiency. And then we have a cascade Kalman filter that goes in and recover the factor. In the second step, we obtain the loadings by regressing the factor observed estimated in the first step. Okay. Okay, and after we have done these 3 steps, data model estimation, we get the empirical results. Okay, so this is what the weekly cycle of the local economic activity factor looks like. If you remember the stylized fact, this looks very much like that. So that we are able to proxy the full line is the total, the sum of the two components, the mean, slow moving mean, and the calendar, while the broken line is just the slow moving mean. As I said, the slow moving mean is absorbing much of the dynamics, but since actually these are still percentage variation, you can see that even the calendar component is adding a lot. And in fact, if we zoom in hour of the day dynamics, so here I'm plotting hour of the day dynamics for weekdays versus weekends and holidays, you can see that actually the difference is huge. So that if you look at the difference in hour of the day from an average weekday from weekend, you can see that you can go up to 52%. And this is taken care of by the calendar components. So that both components, low moving mean and the calendar component are important. But what we are documenting here is that in local economic activity, within a day, you have a very huge dispersion. So that in the bottom of the deepest of the night, you have like a drop, which is about more than 50%, while at the peak of the day, you have about 100%. So double economic activity with respect to the mean going on. Okay. And then again, since we are using all these new alternative data sources, we want to make sure that we are actually measuring economic activity. So we do a bunch of validation exercises. What I'm showing you is the link between our aggregated factor. So when we take the factor at lower frequency with payroll data for San Diego area. And you can see that the cycle that we extract, so our common factor, which is the solid black line, is really kind of proxying the underlying component, the underlying dynamics that you observe in payroll growth in San Diego area. Of course, one advantage of the issue with always with macro data is that they come to be released very late. So in these cases, when you see our factor that can be computed in a sort of nowcast timely way, there's a lot of advantage that you wouldn't be able to get from the uh, payroll data. Okay, so then we show what can we do with all this machinery after we have validated it. So there are many things that one can think of. What we do is that in the paper we have this spatial-temporal economic activity radar, and we do this scenario analysis, forecasting, event detection. So there's a whole bunch of things that one can think of doing. So, for example, the scenario analysis is about evaluating, assessing the impact of local policies. So that if the city municipality is planning some road work, what is the loss in economic activity within a given day? And for example, what we document, again, building on the fact that we uncover, is that there's a very good reason why people should always do traffic work at night, because the impact, if you do it within a day, is kind of huge. These are percentage point of daily San Diego GDP. And it means that if you do road work between 8 a.m. and 8 p.m., you kind of wash away like 5% of San Diego daily GDP. San Diego GDP is 300 billion, so it's larger than Greece GDP. So it means that one day is approximately 1 billion. So if you toss out 5% of 1 billion, is a lot of money, because this is telling you when you should do actually work, okay? Road works. So the conclusions are, in this paper, we push the boundaries of economic modeling and measuring economic activity by proposing this new granular economic framework, where we go in and we analyze economic activity at high levels of granularity, and we document all these stylized facts about intraday variation, hour of the day effects, day of the week, and we document that. Also, we put forward this framework to show how it can be used to evaluate local policies, event detection, forecasting, and this type of economic analysis. Okay, so thanks a lot for your attention. It's a very exciting project, and I like to conclude with this slide that highlights some of the use cases and potential implications that this approach has, and look forward to see. Thank you.